Lagrange multipliers. Okay. Now, so one thing I had mentioned at the end of last time was this. To find a maximum or minimum on a compact, in other words, a closed and bounded set, and by closed, I mean that the boundary of the set is included. Alright, so to find a maximum on a set like that, one procedure that was given last time was this. Find any critical points on the interior. Okay. So that's the usual procedure. You find where the gradient is equal to 0. So what you do is you find all points where the gradient is equal to 0. And if there are any that you find that are outside of the set, you just toss them away. And then you find constrained critical points on the boundary and for that you use Lagrange multipliers. And what you do is your constraints are given to you by any equations that define the boundary. And then finally, you evaluate your function at all the critical points you find in steps 1 and 2. Largest value is the minimum, largest value is the maximum, smallest value is the minimum. Now, there's one nuance to this that I need to mention. Let's suppose that the compact set you're trying to find a max or min on is a triangle, for example. Okay. And we did an example like this a while ago using a different procedure. So what's going to happen is you're going to look for any critical points that are in the interior, just where the gradient is equal to 0, and then you're going to take each one of these edges and that will give you a constraint. So for instance, this could be, for example, x equals 0, y equals 0, and then y equals mx plus b, where this defines the equation of this edge. So you're going to take each of these edges individually and use these as your constraints. And find any critical points. You might find one here, here, or here. So those are candidates for a max or min on a triangle. Now, when we did an example of this involving a triangle, what other points, we found points like this. But what other points did we include? What? Yes, the vertices of a triangle. Now, it might seem like these vertices are not accounted for by what I've described here, but actually they are. Because you have to remember that a critical point is where the gradient equals 0 or what else? Does not exist. So let's suppose that we have a function that's defined just on this boundary, on the triangle itself, forgetting about the interior. Then, so I'm going to draw a triangle, for instance, being in the xy plane, and we're going to zoom in on one of these corners. And let's suppose we have a function that's defined on the triangle. So it's defined along this edge. So here we have its graph for this edge. And then we have the graph for this edge. Now a function is continuous, so these graphs do meet at this point. But even if a function has a well-defined derivative along this edge and a well-defined derivative on this edge, what are the odds that the tangent lines at this point, as you turn from one edge onto the other, you're actually going to have a consistent slope of a tangent line? It could happen. Generally, it's not going to. So what we have here, so what would happen is, if you were to take this triangle and sort of unfold it and look at the graph of this function, then it might look something like this. It'd have a corner in its graph, which means that the gradient of f does not exist at that point. Now, you don't really know if this is what's happening. You don't really know if it's a corner unless you carefully study how the derivative is behaving, or the gradient is behaving at this point. But just to be on the safe side, you might as well just include all of the vertices if you have any. So if you have a set like this that has a nice smooth boundary, no corners, then you can just look for wherever gradients equal 0 anywhere along this curve. But if you are trying to find a max or min on a shape that has a polygon or any shape that has vertices, that's why you need to include them, because there are points where the gradient of a function does not exist. This procedure is described pretty much this way in the Mars and Trauma text, for instance, and they make the point, they don't really emphasize this though, that this is a procedure that you follow when your shape has a smooth boundary. So that excludes triangles. So as long as you take the corners into account, you can still do the same thing. So, if, for example, you have a problem, say, on the second exam, where you have to find a max or min on a set like this, and you have to check a boundary, that's why you got to remember to check the vertices. Okay. That a constrained max min problem, so one that requires Lagrange multipliers, can be viewed as an unconstrained max min problem, except that you have extra variables. Okay. So to see what the equivalence is, suppose that we want to find the max and min of some function f of x, so function of however many variables we have, subject to a constraint that's described by a vector-valued function, g of x. So we'll assume that f, function of n variables, and g, also a function of n variables, but it has m output. So that means that there are m constraints. Okay. So